That would be your sort of classification rule. And this was very nice because it was convex, and we had lots of nice things we could do for logistic regression. Now, as we move to neural networks, basically, the only thing that's changed is now, instead of going straight from the input x to just a single output here, h theta of x, we're going to insert an intermediate hidden layer where the internal node of this hidden layer, each internal node is the prediction of the previous layer of this input. And then we'll have many internal hidden nodes. And so we'll have basically from one layer to the next layer is parameterized by a matrix of weights. And so this hidden layer A is just really just a matrix theta times x, and then put through nonlinearity element-wise. And then this whole thing is just repeated again to the next layer. And so we had, these, again, it's just weights. This matrix from, if you look in the top left corner, we're going from x to a, this weight matrix theta 1, and then a2 to a3 with a matrix a theta 2, and then finally to your output. And so the pattern here, is all just review, of course, is just to go from one layer to the next layer, you hit it by a matrix of weights, and then you put it through a nonlinearity element-wise. And we looked at different nonlinearities, including the sigmoid, tanh, and in particular, the rectifying linear unit, the ReLU operation, which just takes the maximum of x and 0. And so this just sort of summarizes that. You can have as many hidden layers as you want. You can have as many nodes within each hidden layer as you'd like. It doesn't really matter. It will affect the capacity of the network, what functions can be learned, and what sort of functions are most easy for these networks to learn. And that's kind of what we're talking about today, is how do you get a handle on, not so much, and I can't tell you, how deep you should make your network and how many nodes per hidden layer to make your network, but we can talk a little bit about structuring these weights a little bit, and that's today's lecture. And so that was just for a single output for binary classification. But if you multi-class, you of course try to output a one hot vector, like all zeros and a 1 in the k class. For multi-class, it's no problem. Right, and they can do classification, they can do regression, they can do anything, just like linear models can do anything for classification and regression, a neural network can do. And so finally, we talked a bit about like, why do we like neural networks? It's because one reason we like them is because if they're wide enough, or if they have enough nodes, they can basically learn any function. They can approximate, not learn any function. They can approximate any function that you give it. So if you take any function f, there exists some neural network, a two-layer neural network with a finite number of nodes that approximates it arbitrarily well. This is not unique to neural networks. If you run a kernel method with an RBF, this is also true. Assuming, just like this theorem assumes, that the function f is continuous and compact. If that is true, then a kernel function with an RBF kernel, this Gaussian sort of bump kernel, can also satisfy this property. And so you might be asking, like, okay, so I have these two function classes. They both can learn any function. Kernels are convex. Kernel regression, kernel classification. That's a convex problem. We know how to solve it efficiently. We can solve it closed form. Neural networks have this property, but are not closed form, and are very. We need to train them via stochastic gradient descent. And it just so happens that so what makes a network better for something versus another? What makes one model class better for a problem than another model class? Because like, why would we not just use the same model class for all problems? Like, why why do there exist different classifiers? We've talked about linear methods, we talked about neural networks, we talked about kernels. We're going to talk about boosting soon. We're going to talk about trees. Why do all these models exist? And why, is there one that's just better? Is there one function that's universally better than all other function classes? And the answer is no. Basically, and we'll get to this later in the quarter, formally, but informally, there's concepts known as no free lunch theorems. And basically what this says is for any problem for any function class, there exists problems that are good for that function class, but there's also functions that are not good for that function class and need to be learned by some other function class. Meaning that no function class can be arbitrarily good at learning or generalizing all functions. So that was extremely informal and very hand-wavy. But basically what the argument is saying is that if you want to be learnable, meaning you want to be able to learn this function in a finite amount of data, you need to have the function class matched to the problem. You need to have some bias towards the right answer. And that means picking a function class that is more likely, or you're biasing yourself towards functions that are looking like your data. And what that basically means in terms of neural networks is how do we structure the network? Because some structures of networks will learn certain inputs easier than others. So what I mean by that is some networks, be it they being very deep and very thin, or very wide and very shallow, or the way it's being very structured, can more easily learn a function with less data. And so to give you an example of that, because we know that essentially this is also very deeply connected to overfitting, because if you could always throw more parameters and more weights into a neural network, but the more complexity you add to this thing, you will overfit. So basically what you want to do is you want to find the network architecture that is simple enough in order so that it can be learned with a small amount of data, but complex enough to actually learn very complicated structures, but not too complex to overfit your training data.
That sort of suggests, sorry to jump in here for a moment.
No, please.
Yeah. So this universal function approximation is a reason that we really like neural networks, right? There is some architecture in this sort of two-layer network which can, approximate whatever function you're trying to learn. However, to do that, and the fact that that's true means you need a huge amount of data, in fact, infinitely much data, right? To actually find the one which is best for you if you don't know anything about sort of how wide you should make the network, right? And all it says is that there's a finite number of nodes you need, right? You don't know how many you actually need. And if you allow yourself to do sort of arbitrarily many hidden nodes, you're not going to have enough data to learn and generalize well. Right? So that's it's a double-edged sword, right? The better you can approximate any function, the more data you need to learn your function from a given class of models.
I have a question real quick.
Yeah.
So I guess how does the free lunch theorem not contradict this universal function approximation? How are you reconciling these both things?
So this goes to Jamie's point. So let's say you have let's say you have a very, very complicated function class. So you can imagine that the amount of functions is finite in some sense. You cover it, so you've got a finite number of functions. Now, if you have a small amount of data, to distinguish between all of those functions with a finite amount of data is very hard, because you might not have enough data to actually do that hypothesis test of determining which one is the best among all of these functions that could fit the data. And what that means is that if you pick wrong, you're going to not generalize very well. And so what we'd like to have is that the number of functions that you're considering when learning is small so that you can make that statistical decision of among these finite set of functions, what is the best one for my problem. And so what the no free lunch theorem is saying, if you want that property, if you want to be able to choose among a small amount of functions so that you can generalize, that very explicitly means that the total number of functions you're searching over has to be small. To be learnable, you have to be really constraining yourself to a small amount of functions of deciding between. But if you're constraining yourself to a small amount of functions to decide between, that explicitly means you cannot solve all problems simultaneously. Because some functions, because we're only looking at a small finite number of functions if you're trying to decide between, then that very explicitly means that you're not looking at all possible functions. And so you're making a bias. You are making a decision to look at a particular class of functions, and that set of functions may not approximate every function well, but they're learnable. So this theorem is strong in the sense that it says that there exists a neural network that can fit any function arbitrarily well, but it says nothing about learning that function. It says nothing about, if I have a finite amount of data, can I actually pick out the right one among all the possible functions that a neural network could learn? And that is the problem. That's the main problem.
Nor does it say additionally how one might compute such a thing, right? Even if one had arbitrarily much data or, perfect distributional information, it's not at all clear sort of how computationally you could find a good approximator from this class.
Got you. Okay.
So what we're saying then is that we have to constrain these architectures somehow. We have to choose these architectures, and we want to choose the architectures. And when I say architecture, I mean the number of layers, the number of nodes in each layer, and also the allowable edges. What pattern of edges, what structure of those edges are we going to allow? Because every one of those choices is going to constrain the set of possible functions that we can learn. And by constraining the set of functions, we're making it easier to learn. But it's also, learn from a statistical sense, but it's also making it more difficult. You're constraining your classes so it won't have as much learning capacity. It won't be able to learn any function. And so this trade-off really is this bias variance trade-off exactly. With a larger network, your bias goes down, but your variance is going to go up. And so by choosing the different architectures, we can sort of change this continuum. But this is sort of the first sort of example we've seen where there's just a lot of choices you can make, more so than in ridge regression or like kernel ridge regression or anything like that, or k-means. This is the first time where there's like dozens of different choices you have to actually change the network. And that's why, one of the reasons why neural networks have been so such a fruitful area of research is because there's so many questions. So the first architecture we're going to look at, the first architectural unit, is called the fully connected layer. And this is what we've already been basically implicitly been talking about this whole time, where it's just there is some weight matrix. If you have nk nodes to nk plus 1, if you go to the kth layer to the kth plus first layer, there's just some weight matrix theta that maps, that's just a matrix of nk plus 1 times nk numbers that maps ak to ak plus 1 through this nonlinearity. Okay, and so if you think about the number of parameters of this network, if you have big L layers, then the total number of parameters is obviously going to be n1 times n2 plus n2 times n3 plus blah, 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 and so on and so forth. And this is going to get really, really big, really fast, because the number of hidden nodes can easily be in the hundreds. So that like n1 or nk for any k typically will be, in the hundreds, 200 to 300 to 1,000 or larger. And so with those kind of numbers, the number of parameters is growing extremely large. And so this is a concern for a few reasons. One, do you have enough memory to store these things? That's very practical. But two, you have the ability to overfit. It's just a huge capacity, and you might overfit your training data and not actually generalize very well. And so what we want to do is look at different structures that reduces this number of weights, but in a very intelligent way that sort of biases us towards the right sort of space. And to give you an idea, like one way you can bias yourself towards different, like what kind of structures can we take advantage of, is to think about images. So when you take out your iPhone or whatever, I'm not sure if phones do this anymore, but the old digital cameras used to do this, where you'd, when you stick up your phone at a group of people, it would automatically put boxes around people's faces. And it's a face detection algorithm. And this would be nice because you might want to, I don't know, focus specifically for faces and not really care about the background or things like this. But how did it do that? What are the algorithms that it could just so quickly determine where the faces are in a particular image? And to do that, you want to think about, like, well, what if I wanted to do this with, say, like a neural network, or just a hand-rolled solution that you expertly made? And to think about this as a first sort of step in how you would do this, if I want to find Ellen's face, then in the white here, then basically I only need to look at pixels localized in that space. If I said, here's an image without these boxes, and I said, go find Ellen's face, I know that all I really need to do is look in a localized region of this image, meaning like within some, like, it wouldn't make sense to look at a disconnected set of pixels. It wouldn't make sense to have pixels looking in the bottom left to the bottom, the top right, and like be looking at these pixels at the same time thinking, oh, is Ellen's face is in one of these two places? Like, all you'd really do is be looking for a sort of a bounding box, sort of looking over this image, and does this little sub image contain Ellen's face or not? And so this actually hints at what we might want to do when trying to structure these networks. If we're trying to find objects within images, we're trying to recognize people's faces, or whether an image contains a dog or whatever, we might want to structure our networks so that we limit what they actually look at. And so one way to do this is to structure your network, and instead of having all available weights going from the previous layer to the next layer, what you might want to actually do is only have local information passed to the next layer. So on the right hand side here, on the left, on the input layer, the blue weights are indicating that, like, each output node on the right hand side, it's only taking contributions from the 3 closest nodes in the previous layer. And so somehow only local information is getting passed on to the next layer. And this is, in some sense, the strategy that we're going to take in order to encode this kind of localized information into our networks. So from a mathematical point of view, what's going on? And so before going on, is there any questions? I see a lot of activity in the chat, but it's impossible to follow.
I think the stuff in the chat is largely handled. Okay.
So what's going on mathematically is that, again, on the left here, it's a fully connected network where we have just a nk by nk plus 1 matrix of numbers. And so if each layer has n nodes in it, then the number of parameters is scaling n squared. It's a lot of parameters. Now, if we only look at this localized information, so that each output node, so in the middle here, if each output node is only using localized information from its 3 nearest neighbors on the previous layer, then if we count these parameters, it's obviously going to be something like 3 times n. Or if it's like the k local neighbors, then it's going to be like k times n. But this is often going to be substantially less than n squared. But we can do even more, though, because what we realize is that if we're looking to do face detection, if we have some sort of weights, some layers detecting whether a box contains Ellen's face or not. So it's like a classifier. If Ellen's face is in it, then it will output, it'll fire 1. It'll predict 1. If Ellen's face is not, it'll predict 0, that sort of thing. Then if we're dragging this box around the image, looking for where this neuron is going to fire, or where this prediction is going to be 1 or 0, then basically what we're saying is like, well, whether the box is in the top left corner or the top right corner, up or anywhere else, that predictor of predicting whether Ellen's face is inside that box really should act the same everywhere. There's no reason you should have a different predictor for different locations in the image. The predictor itself of is Ellen in this box should be a contained element or a contained sort of predictor, in that you're just sort of changing the location of where that box is going. And that is encoded by weight sharing, and basically mirroring the weights in the different locations. So you still have this structure in the middle here, where you're only getting localized information, but now you're saying, wherever this I'm going to move this box around, and that is encoded by the fact that this pattern of 3 weights coming from the previous one to the next node, they're only looking at localized information. Each output node is a different location in this image, but the fact that the weight, the little vector theta, theta naught, theta 1, theta 2 is just 3 numbers that are like mirrored at every location, is denoting the fact that these are all shared weights. And when we do this, because there's only 3 weights, if in this very toy example, representing this localized information of, say, is Ellen in this box or not, then you're only getting 3 weights of this particular structure. And so we've gone from having n squared weights with a fully connected layer to doing this shared weight structure, where we have this sort of banded matrix structure of shared weights, to just having like order 1 weights. And this is, and really what it's doing is giving us the ability to have encoding this kind of structure of like localized structure going from one place to another place. And I'm talking a lot about images, but like this structure is basically fundamental to signal processing in general. So if you had audio, it's the same thing. If I want to have, if you put in a song, maybe I don't need to have a fully connected network looking at every single second of that song. Maybe I only want to be looking at like localized windows in time, and then within each window, I'm trying to predict like when does a beat occur, or when does a female voice go on, right? If I have that sort of predictor, I only need to look at a little snippet, but that predictor is going to be the same at every different point in the song, and all you're really changing is learning that one predictor of, does this sort of little snippet contain the information that I want? Does it match? If I'm looking for some pattern in the audio or the video or whatever, does that snippet, that localized region, contain the information that I'm looking for? And so what this structure is called, when I have this banded structure like this, where I'm mirroring weights, is actually known as a convolution. And basically it's denoted here. So in math, it is this thing in blue, where it's just a sum of the previous weight of AI, the ith output of the k plus first layer is this inner product between AI plus j, just sort of like the next few elements, just sort of streamed along. This is the mathematical representation. And what you'll see a lot is this notation of this little star operator. So it's so common that convolution comes up so often that it has its own operator, and it's a star operator. It's called convolution. And so we denote that for a filter theta, we convolve theta with the input layer ak, and that itself is a vector, and that's the ith coordinate. I have a little asterisk here because perhaps electrical engineers in the audience might take issue with me calling this a convolution. This is actually called the cross correlation. But for reasons I don't quite understand, the deep learning community has called this a convolution, and it's okay. So just don't get too confused or annoyed by this notational annoyance. And so what we do is so when we see these kind of layers where you have these weight sharing, these mirrored sort of weights, with this kind of structure, we call it a convolutional layer. And so in each filter, we call this vector theta, this pattern that you're looking for as a filter. And we may use many filters per layer. So going from the kth layer to the k plus first layer, what we could have is actually that we could copy this, mirror this for not just one filter, but have a bunch of different thetas. And so you have so within each image, maybe you're looking for Ellen's face, maybe you're looking for a male face, maybe you're looking for, I don't know, a cat or a dog or whatever. You may have many different patterns that you're searching for and might fire when that sort of localized space goes over the particular image. And we'll see a lot of examples in a second to make this sort of more clear. And so convolution, again, it's notated as this for a 1D convolution. So for just a vector of the input vector x in Rn and a filter theta in Rm. Typically, we think of n as being large. So the input is like, your audio sequence of length, say 1,000,000, which is like totally reasonable with a sampling rate of 44 kilohertz. And then the filter size will be substantially smaller, like usually considered like a constant size. So with audio, this may be 100 or 1,000. With images, with like an image that's 256 by 256 image, a filter may be on the order of even like 3 by 3 or 6 by 6 or 7 by 7, not very large. So filters are usually considered to be small things that are patterns that you're sort of searching for in the input. And the convolution, just mechanically, mathematically, is just this sort of inner product like thing where you're taking the inner product of this filter at a particular location in the image, or is it in the vector. And so for this particular input in this particular filter, what we do is pictorially, we just are we're dotting the filter with the input at that particular location. So we get 1 times 1, 1 times 0, 1 times 1. I'm just placing the filter on top of that input. I take the dot product, I sum up all the output, and then I get my first element 2. And then I move over the filter by 1 location. I do the same dot product, I get 1, move over the filter, do the dot product, and you get your output 1. And so what you're doing is you're basically just, to get this output, you are basically just sliding the filter along to try to get some pattern. And at least intuitively, what you're really trying to do is that if the filter has some pattern, when they overlap with your input, if that pattern exists in your input, you'll get a very large response. And if there's no correlation between the input and the filter at that location, you'll get a very small response. That's intuitively what's going on here. And so you can do this with images, and you can basically, instead of a fully connected layer, you can greatly reduce the amount of samples that are necessary, the number of weights. And so, and it's just a simple example with a fully connected with 400,000 hidden units, 16 billion parameters. But if you use locally connected with a 10 by 10 convolutional filter, then you only have about 40 million parameters. And so how 2D convolution works is very similar. So now with an image, very natural sort of 2D matrix, you have some image I, which again, like 256 by 256, and some filter K. Filter sizes for images typically range from 3 by 3 to 5 by 5 to 12 by 12, not particularly large. And then again, in the bottom left, we're just going to sort of move that filter around the image, take the dot product with it localized, and then get this output there. And that is the convolved image. And then up in the top left is the definition of 2D convolution. And so you can get these sort of outputs out. And now the value of images is that you can actually see what these things do.
Hey,
so
Kevin,
convolution, yes.
There's a question in the chat. Brendan raised his hand.
Brendan, what's up?
Yeah, sorry, maybe this is taking your toy example a little too literally, but in that picture where there were the green boxes around faces, the boxes were different sizes.
Yeah.
Is that possible with a filter like in your toy example? Because it seems like that would produce boxes that are all identically sized.
Yeah, so one way, I mean, this is just a toy example, but one way you could do this is if you had different filters of different sizes. So like you don't need to have the same localized structure, meaning like just the 3 inputs going to, or every output node being just 3 inputs. It could be, different output node, or in the same layer, you could have different size inputs going to those outputs.
Okay, so it's basically like there's a green box sitting at every single possible spot, and then some of them are activated, and it's kind of
that's one way you could do this. In practice, that's not exactly what you would do. That's not how these algorithms work to do face detection and these sort of things, because that would be very wasteful to encode every possible size box. But they are typically you would do this with a more image segmentation sort of way, which is super cool. But also very sort of beyond the scope of what we're going to talk about today. But yeah, I encourage you to go and look up more advanced topics. Today, what we're really doing is just giving you the very sort of like 101 to these more structured neural networks. And so, like I said, I've been kind of harping on like these images, these filters are trying to find structure within your image. And so if you have an image here of, I don't know what this creature is, maybe a bunny rabbit. And now for different filters, so convolutions have existed for, this convolutional operator is a fundamental concept. It's intimately related to the Fourier transform. And there's lots of connections between what is the high frequency or low frequency components of an image or an audio sequence or something like this, or any signal. And convolution is sort of the dual, or it's, convolution in the time domain is multiplication in the frequency domain, and vice versa, if that is ringing any bells to those the signal processing background. But what I just want to emphasize is that you can design these filters to do different things. So in the top here, these different filters, if they're designed like this, are going to pick up different edges. So you can design a filter to pick up, basically looking for places in the image where it's going from low value to a high value, or a high value to a low value in different directions. You have vertical edges or horizontal edges, and choosing the right image or choosing the right filter will result in some kind of operation. So edge detection is very popular to do this with. You can also use the sharpen images by just convolving the image with this particular filter, and that'll make it just basically emphasizes. Basically, it's emphasizing the high frequency components, and then different blurs. So like box blur or Gaussian blur, which is just basically averaging the pixels. And so this is like very the blurs make really the most sense, or at least intuitive sense, if you're not familiar with this stuff. All it's really doing is each output location is just sort of averaging its neighbors around that location. So this you can think of the convolved image as being the output layer, where each output pixel is just taking the 9 pixels that are closest to it in the input image, and then averaging them together with particular weights. And so this is one way that we do things. So experts would come up with these filters that are derived from either some Fourier transform or some amount of filter, some loss procedure to output these filters, and they do a particular thing. This is the field of signal processing, and this is how things worked for a very, very long time, where people design these filters to do different things. Another sort of so that's an example where the filters are doing something. They are performing an operation to an image. They are transforming it to look for edges, or to blur the image, or to sharpen the image. It's transforming the image. It's operating on the image to change it into something else. Okay. There's all what these filters can also do is what I was alluding to before, is where each filter can be a pattern, and it's looking for that pattern in the image. So if you're doing a fingerprint, so like how do we do, you know, you always see on CSI, if that's still a show, or like the other like crime shows, like you put your fingerprint into a database and then it comes out with, you know, closest match. How does it do that? That's super weird, because like if you think about an image, if I put my thumb on it, it's like independent of what rotation of your thumb is, what part of your thumb it is, you know, how far up, how far down. How does it actually center and calibrate all of these thumbprints together? Well, one way of doing it is to actually create features, so little filters, so little patches of thumbs. And then what they'll do is they'll run this filter over your image. They'll convolve the thumbprint with this filter, this pattern, and then it'll get some response out, and it will have this very spiky thing. Have a number for each sort of location in this image. And then they can do basically massive downsampling. Just look at the peaks in this image, in a specified in a specific location. See, oh yes, this pattern existed here. Like this pattern was somewhere in the upper left quadrant, and this pattern over here, like this was found in the upper right quadrant of this larger sort of piece of paper. And if it does that enough with enough sort of filters, that's a unique sort of like literally your fingerprint. This vector is just a matching sort of these patterns in trying to find these unique sort of things, or these things that characterize these patterns that characterize your unique fingerprint. Put those into a vector, run those through a database, and literally just do nearest neighbor classification. It will just, because each one of us is going to have a different vector that comes out of this. That's basically the convolution of these filters with your image of your thumb, maybe doing some downsampling to only looking at the maximum response in a particular area. And then we'll each have one of these vectors. We'll do nearest neighbor lookup, and then we'll confirm maybe with an expert analysis. But this is one way how these things work. And so I'm just trying to emphasize that convolution is this very, very core concept in image analysis, and it's used to both transform images, but also has the power to, they're also used for looking for specific patterns, trying to find patterns in the image that are going to create high response in the image. Before moving on, is there any questions about that, about 1D convolution or 2D convolution, the mechanics of it, anything on that?
One thing that's probably useful to know, and maybe many of you have done this, so when you're fingerprinted, right, they actually roll your fingers like pretty heavily, like, so they get, you know, sort of a total picture of like what your fingerprints would be, right? So it would, you could imagine this would be a very hard problem if like somehow you only had like the leftmost version of my fingerprint and you were trying to like, you know, this side of my fingerprint, and you were trying to compare it to this side of my fingerprint, right? The database of fingerprints largely has like a total, like not 360, but like 180 degree like version of your fingerprint.
Yeah. So now I've been sort of alluding to like, okay, now you have these input filters. We're going from like an input layer to an output layer. But when we're talking about images obviously have structure. So like they have 3 channels, R, G, and B, red, green, and blue. And so they're not just 2D matrices, they're actually 3D matrices. And so I'm calling this 3D convolutions, but it's really like 2.5D convolution. Because basically what this is doing is you're still moving sort of filter around this image in 2D space, but because that input image has depth to it, meaning it has 3 channels, color channels, the filter that you're moving around is not just 2-dimensional, it's actually 3-dimensional. And now what you're doing is you're just taking an inner product of this 3-dimensional tensor with a at that particular location and then moving this around. And then usually the depth one is always the full width of the convolution. And so that's why I'm saying it's more like 2.5D convolution. If it really did move, if the depth sort of dimension of the filter was not equal to the input depth, then you'd really be moving this 3D block around the tensor, and then it would be true 3D convolution. But this is fine. And so what's the output of this thing is you're moving this sort of 3D block around in this 2D space at different pixel locations, and then it's taking the dot product. So the output node is just this dot product of this 3D matrix or tensor. So I kept using the word tensor. A tensor is nothing but a generalization of a matrix. So a 1D tensor is a vector. A 2D tensor is a matrix. A 3D tensor is the cross product of 3 different dimensions. So it's basically adding a dimension to a matrix. And so you can have arbitrary dimension tensors. And so each output pixel of this convolution is going to be the inner product of the 3-dimensional block with the 3-dimensional block in the input image or whatever, and then outputting just a single pixel, which is some number, and then we're going to move this around the image. Okay, that will get you a single output channel. So I'm introducing this notion of channels now, where you have 3 input channels in an image because it's RGB, and then you get 1 output channel, which is just this output layer. But this is just for a single filter. Right, so now I can repeat this process for multiple filters, and each filter will result in a different channel. And so if I repeat this D times, I'm going to have, so if in each output channel, so the depth of this, if I have D filters, then I'm going to have an output instead of 27 by 27 by 1. If I repeat it with D different filters stacked on top of each other, I'm going to have 27 by 27 by D. And now I have this 3-dimensional tensor again as the output. And what I can do then is throw that through a nonlinearity and perform this again. But instead of having this 3-dimensional tensor can be the output, this 3-dimensional tensor can be the input to the next layer. And so instead of having just 3 channels like an RGB image, we're now getting very comfortable with the fact that we have sort of this spatial dimension of the location of the image, but then the depth of the number of channels within each caused by the number of filters. And so then we can go from D filters to P filters in the next layer and perform this convolution. So to give you an idea of what I mean by this, so if you have some, yes?
There is a question from Ariel.
Okay, go ahead.
Yeah, I noticed that your picture went from 32 by 32 by 3 to 27 by 27. So is there some amount of like width lost by kind of going over this with the matrix?
Yes, thank you for bringing that up. So it depends how you define convolution. The way I've defined it here, as you note here in the top left of the equations, I haven't actually told you what the indices of M and N are, or like what the limits of these things are. This particular, what I'm showing here is the filter is completely enclosed in the image. And so what's going to happen here is because the filter is completely enclosed, in the image, the output is necessarily going to be smaller. And there's a very simple formula for determining this, how much smaller it's going to be. I think it's n plus n minus 1. If you started on the outside, but if you start within the inside, then it's something else. I believe I'm not even going to guess. I'm not going to try to do this in real time, but it's not hard to work out exactly the formula for what the output size is going to be if you do this internal size. But this is not standard. I mean, like, there is no standard. Many people will do this sort of downsampling like this. So like they'll only have the filter go on the inside. So the output layer is a different size than the input layer. This is an annoyance for some people. So sometimes what they'll do is on the input image, they'll actually add zeros around the border of it. Because if you add just one layer of zeros, this is called zero padding, then you put the filter on the inside of this augmented image, then the output image will be the same size as the input image. And so if that's a desired property that you'd like, you can do that. And it often makes almost no difference in practice, but can be, sometimes you want to do it so that your input images, your output is the same size as your input. Sometimes you just don't care, and that's it. And so that's why in this picture here, when we go from a 32 by 32 pixel image, we're going to a 27 by 27 pixel image because we're convolving with here a 6 by 6 filter. All those numbers are there. And so if you're to do that, plug it into the formula, you'd get that the output's going to be 27 by 27 instead of 32 by 32. Does that clear that up?
Yep.
Cool.
Another question from the chat. In this slide, is the R any related with the D, the dimension of the image?
R, is the R related to the D?
Oh, so R here is the number of channels on the input. So here, the number of input channels is 3. And so the number of input channels is 3. So R is equal to 3. And then the number of output channels, because I'm doing this for D times, so D different filters, the output channels is D. So the input channels is R, or input channels is equal to 3 here in this example, and the output channels is equal to D. And so the that is how they relate. Hopefully that.
Okay, yeah, I was just wondering if like D filters were for D channels, or it's not for the channels. It's, you just have filters for different, how many sliding windows there are. Whereas
yeah,
R
so
is
each output, so each filter corresponds to a different output channel. So when you convolve an image with a filter, you get one output channel. And if you do this D times, you have D output channels.
Okay, so is there one output channel, I mean, one output filter per channel or per something else?
There's a one-to-one correspondence between output channels and filters. The
Okay,
filter,
so,
the filter creates the output channel. So
right, okay, so
D filters, you have D output channels.
So D is equal to R then in this?
No. R is the input channel, is the number of input channels. So the number of input channels is 3 here on the left in the red box, because the input was an image, RGB, so 3 channels. And then it was for a single filter, so R is equal to 3, and it outputs to a single output channel. One filter outputs to a single output channel. And I'm going to do this with D different filters. I'm just going to stack D filters. And so I get D output channels. And each filter is, in this case, 6 by 6 by 3, for R is equal to 3.
Okay, so the number D is determined by how many sliding windows you have.
Yes, the number of filters.
Okay. Thanks.
And so what this looks like is for each input image, you're going to slide your filter along. It's going to output the first output channel. And you use many times. And each one of these different filters is going to result in a different output channel here, which this is called feature map. And then once we do that, for each one of these output filters, again, we need to do one of these nonlinearities. Because if you look at convolution, if you look at this operator, that is just linear, right? That is a linear operation. Convolution is a linear operator. There's no nonlinearity in there. And so if you just stacked a bunch of these layers together without any linearities in there, you are not doing anything more than just a single matrix multiply. They can all be collapsed into a single matrix. And so what you need to do between each layer is just like with neural networks, you need to do a nonlinearity. And so what's very common, a very easy one is ReLU, rectified linear unit. And so for each output channel, corresponding to each filter, you're going to then take the ReLU, operate the ReLU on top of this image, and only take basically the positive parts or the non-negative parts of the image. And then now you've got an output layer, this 27 by 27 by D or 64 thing here. So you've now got an input to your next layer where you've got 64 by 64 by, or sorry, 27 by 27 by 64 channels. And now go into your next layer.
There's a hand from Dino in the chat.
Yeah, sorry. I think I've Tobias just answered the question, but I would still like to go back to it because I think I got it wrong. So my interpretation originally was that you apply each filter to each of the channels, and then you get a filter applied to a channel out. But it seems that you apply filter to the whole image with all 3 channels, and then you get one layer out, and then you stack the layers, right?
Yes, what you said, the last thing you said is correct.
Based with this definition. All right. So I'm just saying, is this standard in? Is this like widely accepted standard in machine learning field?
Yes.
Okay.
So if you do, so the reason I call this 3D convolution, I'm really regretting that now, because it really is just like 2.5D. Because
the reason why I'm asking is, from my experience from other code like OpenCV, etc., really not allowed to mix the channels. So if you wanted to do something like, you wouldn't be able to do that.
Yeah, no, that's a really, really great question.
Okay.
So in something like OpenCV, that's a traditional sort of image processing library. And so that's more, the bread and butter there is more like these kind of filters and like other features like hog and stuff like this we're going to talk about in a second. And so there, it's like, look, I can really only think about performing a filter on each layer, on each input channel individually, and getting something out, and then just adding them naively. Now, what we're gonna, but like by mixing the input channels, which seems weird, and like would be very hard to sort of think about from to expertly create filters like this, what we're going to do, basically these are the weights of a neural network. So the neural network is going to be able to learn these thetas. And because they're learned, they can learn things that we just don't know how to intuit. And so we'll find that you get a huge benefit by mixing the input channels up with a single filter, and you get something out that's very meaningful. And it does make sense. I mean, it makes sense that like you should be mixing the channels in a very smart way. And so we'll see that in a second. But yeah, mixing channels is very standard in modern deep learning frameworks like TensorFlow, PyTorch, etc. And this would actually be called a 2D convolution there, because again, it's more like 2.5D. So
there's another question in the chat that I think is a good one to answer. So when you apply the nonlinear transformation, what is the dimension of the output, right?
So we're going to apply the nonlinearity element-wise, just like we did with standard neural networks. And so our output layer here is going to be a tensor, 27 by 27 by D tensor. And now when we apply the nonlinearity, we're going to apply it element-wise. So for each element in this 3-dimensional tensor, for all ijk, we're going to just take the nonlinearity of that individual element. So with the ReLU, you just take the max of that number and 0. Okay. And that's exactly done. Pictured here in the bottom here. You just look at each element ijk, and then this is a single output filter or single output channel. You look at each element, and you take the ReLU of it. Okay, so now going back to something I alluded to a minute ago about finding fingerprints, like finding like, oh, well, you know, my thumb is not calibrated in the same place every time. If I shift it over by just a little bit, the location of that particular element is going to move a lot in vectors, in like index space. And so what we really want to do, we want some structure that will say like, this filter got a very high response in this particular part of the image. Like in the upper left quadrant, somewhere in there, it had a high response to this particular filter. I don't know exactly where, but it's somewhere in there. Because we want to basically get rid of this sort of translation. We want to be translational independent in a sense. We want to sort of summarize information from the image or in a particular space into some smaller particular space. And I keep using images because it's very convenient, it's very intuitive, but like basically everything I'm saying will always translate into arbitrary signals. Typically, you're always going to want to be working locally within a signal, be it audio, be it video, be it images, or even a scientific experiment. Typically, you want to be looking at local information. So one way to do that is to just do a pooling layer. So the simple one is a max pool, and all it does is it just basically is a downsampling step in a sense, where is a 2x2 pool, max pool. What it'll do is it will just look at each 2x2 block and then take the max of that element and then downsample the image by a factor of 2. And so this is very nice because what it's going to do is it will reduce the dimensionality of your object, of your input tensor. So if you had a 27 by 27 by 64 input tensor, after a max pool operation, it will go down to 14 by 14 by 64. And again, you can add zero padding and stuff like that to this to make the dimension sort of a little bit more nice. But this will always sort of implicitly be reducing the dimension by some factor. So if you do a 3 by 3 max pool, you'd be reducing the dimension by 3. And so combining these, so in addition to max pool, there's also average pool or sum pool. The list goes on. Max pool is tends to work as well as anything else as average pool, but these are options. And so putting all these three sort of things together, what is very common is to have sort of an input layer. So let's say an input image, for example, with a 32 by 32 by 3 channels. You do your convolution with 64 filters. You get an output tensor of 27 by 27 by 64. You perform a nonlinearity on every single output channel. And then after that nonlinearity, you will then perform a max pool, which will reduce the dimensionality of that particular output. Okay. And then once you did that, you can then take that 14 by 14 by 64 matrix and just flatten it into a vector. And now you can perform typical machine learning stuff. So going back to that fingerprint example, you would perform, you'd have these, instead of 64, maybe you have like 64,000 filters, which are just unique sort of patches of what little tiny pieces of fingerprints look like. And it will, you'll get tons of different output channels for each one of those, for each input image. You'll then do a max pool, which will then say like, oh, that filter really had a huge response in this upper left-hand quadrant or lower right-hand quadrant. It's pooling information together. And you could do very, very aggressive pools. That, this is a 2 by 2, so it's not that aggressive. But you could literally do like, you could reduce the dimensionality by 27 by 27 to a 2 by 2. That's actually very reasonable. To just be able to say like it's in the upper left quadrant or the upper right quadrant, something like this. So then you get these responses out, and you just vectorize them. You flatten it into a big vector. Now it's a feature vector. And you can use this feature vector to do nearest neighbor lookup. You can cluster based on this image, based on this vector. You can put it in an SVM. You can do anything you want. And the point here is that you've transformed an image, which is very complicated object, which has lots of structured sort of information in it, like someone's face. You've applied different filters to it in this very structured way, and you've removed sort of spatial information by the max pool, and then you've turned it into a vector that then you can use in any machine learning application. Okay, and so this last layer is sometimes called these these operations though of taking conv layers and max pooling and ReLUs. That is like it's a block that you can apply over and over multiple times before getting to this final output layer of one sort of output vector. And what you can think of is these series of operations are just getting you or featurizing your input into a better feature map. It's really just a fancy way. We talked about H's before, like H of X to transform your feature into non-linearities of your input vector to some better space. This is some way of it's a good way of thinking about what's going on with these neural networks. At least these convolutional neural networks is transforming your image, which is a very sort of difficult thing. If you just plug that into an SVM, it wouldn't do very well. But it's transforming your image into a more usable vector that can then be used by standard machine learning stuff. So this output layer at the very, very end of this thing is often called an embedding layer. And basically it's a representation, it's a reparameterization of your image into a more usable sort of form. And again, I've been talking about images, but this applies to any kind of signal. These are just fundamental operations on the space of signals, and anything is a signal. Any sort of data is a signal.
Kevin,
and so
there's a question from Ariel in the chat.
Yeah, I had a question about, so I understand that you can flatten this into a single vector after your max pool operations and such. So why don't we flatten the original 3 by 32 by 32 vector into, or matrix kind of into a single vector? Do these filters kind of, you use certain filters to look for certain things and encode that sort of information, and that's why it's more effective to filter first and then flatten?
Yes, precisely. The filters are picking out specific structures in this image. They're looking for big responses in the image, looking for particular patterns. And then the max pool is trying to get rid of location information. It's trying to summarize what's in the image. So if you apply max pool, a sequence of max pool layers and convolutional layers, you're going to basically take this very structured 256 by 256 image and basically get more and more, you're getting rid of that spatial information and just getting into a vector that's hopefully representing things like, yeah, a dog was in this image, or a giraffe was in this image. I don't know where, or maybe that information is also encoded in this vector, but like it's trying to take this image where it's a very horrible representation. If I were to shift the image by a pixel or two, that could completely change your output if you just put the raw pixel image into an SVM or something like that. And so what these transformations are doing are trying to get, trying to be translation invariant in a sense, trying to get better features out of this image. It's a feature extractor. And so maybe ask your question again at the end if I don't answer this more sufficiently, because we're still getting to it. So OpenCV was mentioned a minute ago. This is a package that makes image processing and video processing convenient. It was a collection of tools to do this sort of thing. And one thing that was always implemented in these image processing toolboxes is hand constructed features. So where do these filters come from? These 64 filters? People would come up with these. So people would come up with clever ways of coming up with different filters and then different nonlinear operations and different max pooling type operations. But convolutions are always there. You convolve and then you do something. Either you're looking for edges or directional edges, like what direction are edges going. You're looking for particular normalizations in the image. You're looking for particular edges or curvelets or wavelets in this image, like hog or texon features. And basically, you're trying to transform your image into a different basis. And that's what a lot of these hand created features were doing. And now, but in deep learning, what they've done, what basically we've said is like, okay, these conv layers are really just neural networks but I've severely restricted the set of weights, set of edges going from the input layer to the output layer. They all can be written as just a matrix, just like we had before, but I've now said some edges are 0 by just taking them out. And so I can train them precisely the same way. I can train them with stochastic gradient descent. And so what instead of trying to come up with hand-created features or hand-created filters, which still makes sense, from the context of things like edge filters and things like this, what deep learning is doing is just saying, well, you know what? I'm just going to let these be hidden variables, like hidden variables as if they're a weight vector for my linear regression, and then learn them. So I have some output. I'm trying to classify an image as containing a dog or not. And what I'm going to do is actually just take gradient descent on these unknown filters and try to learn them. And so instead of trying to create these filters by hand, a neural network is actually trying to learn these filters to be as useful as possible, the most compact representation as possible. And so this gets back to an earlier question about, like, are you allowed to mix the input channels? And like, yeah, why not? If they're being learned, if there's some complex way that the input channels combine to get some some desired output, maybe it'd be hard for us to handcraft that feature. But if you're trying to learn it, it could probably be learned by stochastic gradient descent. And that's indeed exactly what happens. And so sometimes these filters are incredibly intuitive. We can look at them and they look like something. Other times not. But one thing that's popular is that you can actually visualize these layers. You can see what filters are actually being learned and what is the relative output at each layer. So this is just a very old network, LeCun or LeNet, by Jan LeCun. Basically, this is just one of the simplest possible networks that we've been discussing here. You first have an image. You do a 2D convolution to get a bunch of output layers, output channels. Apply a ReLU. You do a max pool. You do convolution with a ReLU. You do another max pool. Then you output to a fully connected layer, and another fully connected layer, and another fully connected layer, and then the output. Okay, and so this sounds like, wow, okay, a lot just happened there, but like not really. Like it's really just taking advantage of the structure of convolutions, and then you get back to this after the output of the last pooling layer. That's sort of this feature vector embedding that we were just talking about. And these final couple layers of fully connected layers, that can be thought of as actually just an arbitrary learning algorithm. So like you could have put a kernel there in the last few layers and it would have been fine. Because the first few layers of convolution and pooling, that's what's doing all the featureization. That's what's turning your image into a vector that can be used by any machine learning sort of algorithm. And because you're already using neural networks to learn the weights, it's convenient to have these last few layers be a neural network, a fully connected neural network. And that's exactly what happens here. You can do things where you never actually introduce a fully connected layer. You're just doing conv layers the entire way through. That sometimes works. And the actual structures get much more complicated. There's things like modern networks like ResNet or DenseNet. They have different structures for exactly how, more complicated than just a convolutional layer. But more or less, they're doing something like this. It's very similar. And so looking at a data set that you're all familiar with, MNIST, one thing you can do is actually look at these output channels. So if the input channel is just I think it's a 28 by 28 by 1, it's grayscale, right? That's what the data set is, so these digits. So if you take this 8 digit as input, then the next layer up here, that's the output of the convolutional layer. And so each one of these 8s on the second layer here is each output channel. So you have 8 filters, just an example, and you have 8 output channels. And that's what the output channel looks like when you put in this 8. And so you can kind of intuit what these filters are doing is in this case, it looks like it's looking for edges, vertical edges, horizontal edges, and just gradients in general in this image. And then on the next layer on top of that is doing a pooling. So now it's downsampling, it's doing a 2x2 sort of pooling. So it's just dragging on a 2x2 block, just taking the max element. And that gets you the next layer. And then once it has a pooling layer, it still kind of looks like images. You're going to do another conv layer. And then that's the next output layer there, where it's starting to look like nothing or not much. But again, if you really squint hard at it, you can be like, oh, I mean, it's not doing nothing. Maybe it's looking for edges in particular directions, something like this. Well, then you do a pooling layer again. It looks like garbage. Doesn't look like anything. But then it goes into a fully connected layer. And now at this fully connected layer, this is just an arbitrary vector. There's very little structure in this. It's very hard to see, if you can't really look at this last pooling layer and say like, oh yeah, that's definitely an 8. And really what these convolutional layers are doing are trying to transform something that looks like an 8 into a vector that's gotten rid of spatial information. And it's really just encoding what is the semantic information of this image. What is this image? What is this image of? And that's the input to this fully connected layer. And then these last couple fully connected layers are really just trying to map that embedding layer, that representation of the 8 into the classification task, which is predicting 8 instead of 0 or 2 or 1 in this classification model. And so is there any questions on this diagram, what it's all showing?
I just have a question. This one is clear, but it's hard for me to wrap my mind around it's hard for me to wrap my mind around how is this kind of like translation invariant, like if the 8, okay, all 8s look the same, but if I kind of shift the 8 a little to the right or to the left or something, I'm just I would, in my mind, the FC layer would have a totally different vector than
That's sort of the beautiful part. That's actually where max pooling comes in. It would actually look very similar, because if you did shift, as a thought experiment, suppose you did shift the 8 1 pixel to the right. So then all of the images above it would be shifted to the right. But then when you did the max pool, because the max pool is doing a 2x2 max pool, is summarizing 4 pixels into 1. Actually, the pooling layer wouldn't change. The output of the pooling layer would look exactly the same if you shifted this over by 1 pixel. And that's the point. It's that these pooling layers are somehow trying to introduce this translation invariant piece. I say translation invariant and I kind of cringe because it's not really doing that, because it's still maintaining spatial information in this upper left-hand quadrant or this sort of general area, but it's still doing a lot of summarization. Each max pool layer is reducing dimensionality and summarizing the information that was in that area. And because each filter is acting the same at every local location, you actually are, if you were to translate the 8 by some amount or rotate even, you should basically the output should not change that much.
Got you. Okay. Kind of remarkable.
Yeah. Any other questions? Okay, then, so convolution is a fundamental operator. I've talked a lot about images today, and it would be a huge mistake if the takeaway from this lecture is convolution is really just useful for images. Convolution is a fundamental operator for any kind of signal. If you have audio, if you have video, if you have just stock market signals, the paths of a stock market, any kind of time series, you would run convolution on it, because that is anything has time in it, anything has a spatial dimension in it, you would run a convolution on it because it's a fundamental operator. And then pooling is really there to reduce the dimensionality and summarize the information. And the last few layers, once you featureize it with all these conv layers, then you can use a fully connected layer, just as if you would use a kernel or anything like this. Really just that sort of thing. And what I want to emphasize here is that while you can learn this this way, I also attached on the website, we talked about different filters, like expertly crafted like these. You can learn them through neural networks. And one that really surprises people is that you can also just randomly set them. So I can take a filter, if I have these 10,000 filters, I can literally just either initialize them with Gaussian random noise and then convolve them over the image and then get this output layer and pool, take nonlinearity, and then gets this one sort of, so this exact framework right here, and get this one vector output, and then just do linear classification on it. Never train the random filters that we initialized. Convolution is such a fundamental sort of operator that that random initialization, you're just looking for random patterns. You can, and then, so there's no training of the convolutional layer, and now you've got a convex problem. And so the attached paper by Andrew Ng and Coates and Ng basically had this sort of idea, and there's been follow-up works on this sort of regard, where like you can actually do this very simple operation. If you don't have filters, it works, and you can get very, very close to you can get reasonably close to state-of-the-art performance doing this with enough filters, and if they're initialized in the right way. So you can do random patches of images of your training set, or you can take just Gaussian random noise. And the Gaussian random noise is a particularly nice one because you can actually show that this sort of random noise filters with a ReLU is actually a kernel, which is a nice sort of connection there, which is obviously like totally not obvious that that's what's going on, but you can prove this. And so you're going to have a homework where you will be able to work on images, CFAR 10. And in previous years, I've had this competition where you can use as deep layers as you can, and you're competing with me, where I only get to use random features and an SVM, and I've very rarely been beaten. So it helps to be clever and think of just the power of basically convolution. It's really just a featureizer. And then once you got your features, you can do whatever you want. So that's it for convolution. Next lecture, we'll see a little bit more about, modern networks are very complicated. They have lots and lots of hyperparameters, meaning like the number of layers, the number of filters within each layer, the size of the filters, are you going to do data augmentation, which is like, do I put rotations of images in the same, do I rotate my images so that because that should have the same label or not, maybe do a mirror image of a label image. Do you do batch norm? Gradients explode or they go to zero? Normalizing the batch gradients is a thing. Do you do that or not? Sometimes you don't do just a ReLU, the max of zero in the number, but you also use ReLU linkiness where you have some slope. Because they're non-convex, so you use a learning rate schedule. So you'll have some step size for some amount of time, and then reduce the step size, then reduce the step size. A lot of decisions to make here. How do we make these decisions? How do we do this in an intelligent way? And then a little bit more on how this connects to unsupervised learning and supervised learning next time. Okay, thank you all. And we'll stick around for questions, of course.
Hi, I have a question that's not related to convolution.
Okay.
That's okay. So let's say I have a panel data in which I, observe individuals by time.
You have what data? Sorry.
We say, like in economics, we say it's panel data, PANEL, panel.
Okay.
But it's just a type panel, yeah. So it's just the data in which like we observe individuals over time. So
okay.
Yeah. So like we know a lot of methods that work well with cross-sectional data, but like if you wanna predict the individuals, in a panel data setting, like what should I be aware of, like be careful about? I know it's a really abstract question.
I mean, I'm not aware of the particular structure of panel data per se, but I mean, if what I'm hearing, it sounds like it's like a time series of where people are evolving, their views are evolving over time or something like this. That's if it's any kind of time series, convolution is a very reasonable thing to be doing on that. But if you're trying to predict the future from this time series, it gets a little tricky. I guess it really depends on what you're trying to do specifically. This might be a question that's better suited for office hours, though.
I see. Thank you.
I have a question about your last point about like the random feature stuff. What do you do, like, so you said that you beat everyone who like uses neural networks, right? Like, what do you do with like, so what are you doing with like random features so that you can beat like arbitrary like depth layer like neural nets from people?
Yeah, so it's really easy, at least on CFR10. Like, this does not generalize to ImageNet, like larger, harder data sets. But I mean, it does a little bit. You know, like 85%. I mean, it's pretty good, but it's not like near state of the art. Basically, you do random patches in the data set. So you take random sort of patches of 7x7 or something like this from your training data, from the images, and you use those as filters. Because like if I'm trying to detect airplanes, if I take patches from airplanes, there's probably going to be a tail piece in there or a wing piece in there or something like this. And so when it goes over that image, you can have a very high response. So you take patches, random patches from images. You also throw in some additional random features to get like, what's going on. And then you will repeat this about 100,000 times to get an enormous feature vector. It'll just truly be unbelievably large. And then you can run your ReLU on it, and then you can run lasso on it, or you can run just your typical linear regression. Or if you're feeling, adventurous, you can do a kernel RBF if you can fit it into memory. And so if this vector is like 64,000 by 64,000, you can, if you've got, a terabyte of memory, you can compute the kernel matrix, you can do kernels on it, and it will do very, very well.
Got you. Okay. In terms of like production grade, like can those like methods compete with the state of the art, the ResNet, whatever, like the complicated stuff that you had in the real, like, can those methods compete?
I mean, on smaller stuff, yes. On smaller, simple problems. But like throwing a neural network at it is probably going to be simpler. And so, I mean, that's really what you should be doing. I just want to make this last point that like, if you do think a little bit about your data and you are a little clever, like you don't need to, like the convolution operator alone is so sort of featureizing that you can get away without, you can do very good things without requiring a deep net. But oftentimes, what people do in practice is Google will train some enormous network on images, or Facebook will train a neural network based on like all the images on Facebook, okay, to do like something, and some unsupervised learning task or self-supervised task. Then they'll publish that output layer. So basically, you can push any image through that network, and it will output a output layer that's of size, 1,000, right? And then you can use that in an SVM or in a couple layer neural network or anything like this, and it will work amazingly well, because what data is giving them is basically a really, really good featurization of images. And even though they trained on faces or Facebook images, if you apply this to like biological data, or like whether there's a weed in this image, like a John Deere tractor looking down at soil and like plants, is there a weed in this? And then like doing classifier on that, like it'll work. It's just amazing. That like, and it goes back to this idea of this image prior idea. That's basically saying that all images live in a very, very low dimensional space, in the space of what you could make a matrix out of, like a matrix of pixels. And so what this is, the theory here is that why these deep nets are getting such great representations and translate so well to other tasks is that they're learning just a better representation of that image space. So all images live on some manifold, and they're finding some parameterization of that manifold. And so that you are sort of, when you're looking at those 1,000 dimensions, they're basically, you're moving over this sort of like curved map in this high dimensional space and making sense of it. So that's a lot of times what people do. Like if you have a startup or something, you just take some pre-trained network and then just use the output and train, fine tune your network, just the last few layers on the outputs. And it works well.
Has anyone ever seen kind of like, so you have like a lot of these hand engineered features that are like, you know, a lot of, you do, you know, like it's very, I guess, theoretically motivated. You kind of are looking for some specific thing. Has anyone ever kind of seen, you know, those kinds of handcrafted features in trained neural nets? Like that's the kind of feature you see, you know, these nets extracting?
Yes, very much so. So like this network, this LeNet data, if you look at the filters on this first layer that come out, you just visualize what they are, you'll find they look exactly like things that called Gabor filters, or very natural sort of signal processing filters, kind of look like wavelets. Right. And it's because, I mean, they're just sort of fundamental operators. It's going to, all these filters tend to look like low pass filters or high pass filters or band pass filters, because those are fundamental sort of elements of image processing. And so this shows up over and over and over and over. They absolutely do look like things. However, the next few layers, as you get deeper into the network, funny things start to happen. They actually start picking out specific structures in your data. So like you'll literally see, like you'll look at filters and it'll literally be like a filter that looks like a dog, or like looks like a cat, or looks like a different shapes, or looks like faces. And it's just bizarre because as you go deeper and deeper, the lower layer, so the layers closest to the input are just really just trying to fundamentally just transform your image into something workable and getting like the rough structure, rough sketch of it. And the deeper layers are really actually going after specific objects. Right? There is like a clown filter and a dog filter and things like this that start to show up. And this is actually kind of scary. Maybe we'll comment on this later. The fact that a lot of these neural networks are actually memorizing the training set in some ways. Like you'll actually see filters start to look like individual training examples. And I just mentioned that Facebook and Google will release their networks. This is somewhat of a major privacy concern, that these neural networks are being trained on people's data, and sometimes the network themselves, the weights, are actually capturing individual people's data. And this is a major concern. And so differential privacy and just privacy preserving learning methods have been proposed to address these kinds of issues. But there's always this fundamental trade-off of, if you want your classifier to be private, you're fundamentally you're constraining your space. So it's going to be harder. But on the other hand, there's also these theorems that say like, well, if you're private, then you generalize, and if you generalize, then you're private. So it's a big can of worms these days.
Cool.
I don't know if Jamie has any follow-up on that.
Not hugely. I mean, yeah, it's pretty interesting. There's definitely some work that shows, you know, you can basically recover images from your training set for certain kinds of networks, right? Which is sort of shocking. if you haven't seen it. So like it's kind of fun to go take a look at those. Yeah, and right, I guess what Kevin was saying just a moment ago is sort of, in some formal sense, if you're not doing something that sort of is private, there's some sense in which you're not doing something which will generalize well. That's not quite right, because there are definitely things you can do that are not differentially private that will generalize, but like it's a natural way to argue about generalization, to like sort of show you're not like so overfitting some of your training data that you could exactly recover it from the neural net.
Thanks.
I have a question about convolution. So for the 3D convolution, we repeat with the filters on image. Is it unique for 3D convolution, or can we do that with 2D convolution and 1D? And is that
yeah, absolutely. If you're doing 1D convolution, you would absolutely repeat with many filters, and to have multiple output layers. So yeah, so like in this sort of toy example, we're just outputting one. This is just one output channel with one filter, but then you'd repeat this many times, and then you'd have a two-dimensional output. If you had the input vectors and Rn, so one channel, if your input was one channel, and you repeated this D times with D different filters, you'd have a D channel output.
Okay, got it. Thank you.
Kevin, I have a question about when you were talking about the no free lunch theorem earlier. You seem to use the terms like fitting a model and learning a model differently. Are those do those have like different meanings, or are they used interchangeably?
Good question. I think I was being very informal, so I was probably using them interchangeably. But typically, fit corresponds to fitting data, and I can always fit data arbitrarily well. But the true function that data was drawn from, I may not learn that function very well. So maybe I was making a distinction between those two different concepts. Just because if I overfit to the data, I will not learn the true underlying function that generated the data, but I will fit the training data arbitrarily well.
Right. Okay, cool. That makes sense. Thank you.
And we'll talk more about no free lunch and pack learning later.
Cool.
Okay, then we'll see everyone Monday and talk more then. Okay, see ya.